All right, welcome to lecture 12. In this lecture, we're going to basically go over some of the properties of continuous functions. So we're essentially going to be proving theorems of the form, let f be a continuous function, then, we can say something about it. So the first property that we're going to look at here is the fact that on closed intervals, continuous functions are bounded and they achieve a maximum and minimum value. This is actually a surprise. It seems like it should be obvious, but it's a surprisingly subtle concept, especially because if you drop, even the closed part of the closed interval, and you just look at like an open interval or even like a half open interval, everything goes out the window, and a continuous function can be very badly behaved on most sets that aren't just closed intervals, basically. So we'll see a bit more how that's possible in a bit. But so let me just state the theorem, and then I'll kind of draw a little picture to explain where the idea comes from. So this is theorem 18.1. So let f be a continuous function on a closed interval AB, then f is a bounded function. So f is bounded. When we say f is bounded, that means that there is some number, capital M, such that the absolute value of f is less than or equal to capital M for all x in the domain of f, or at least for all x on the closed interval AB. Okay, yeah, and also let's see. Achieves its maximum and minimum values on AB, i.e. there exist x naught and y naught, or, okay, yeah, that's the notation they use, such that f of x naught is less than or equal to f of x, less than or equal to f of y naught for all x in the interval AB. Okay, so yeah, x naught and y naught are just the, I'm gonna just change this from the book's notation because I don't really understand why they do it like this. I'm gonna say maybe x1 and x2 or something. I think it's just misleading to use a y here. Or, yeah, people are really used to thinking of y as the value of f. Anyway, so x1 is the location of, or one of the possible locations of where f achieves its minimum value, and x2 is one of the possible places where f achieves its maximum value. So there exists at least one, there's at least one value of x for each one of those. So before we actually do the proof, so I just want to kind of sketch the idea for you. So, all right, I decided I needed a new page for this, but I'm going to try to sketch the proof idea. So, proof idea. Let's imagine trying to construct an unbounded continuous f on AB. Okay, so I'm gonna draw, here's our function. Okay, or, well, yeah, here's the x-axis. Okay, here's A, here's B, and we have this closed interval, right, on the x-axis. And then I'm gonna draw Okay, let's just imagine we start with like a constant function. Okay, here's how I imagine going about the process of trying to construct an unbounded function. Okay, so we start with a constant function, and then we try to we create, you know, we could sort of deform it to make a little bump to make a place where the value of the function is bigger, right? And basically what we're going to try to do is keep adding in spikes in the value that keep getting bigger and bigger and bigger. And we want to, you know, do it in a way that preserves the continuity, basically, right? And we want the spikes, we want there to be like an infinite number of spikes, basically. So the spikes have to get like taller and taller and taller. So let's say, and I'm unfortunately not going to be able to erase this bottom line very easily. So I'm just going to kind of draw the spikes on top of it. So let's say we make a little spike here, okay? So now we need to add another spike that's even taller than that one. And we can try to make them thinner and thinner too, right? To give ourselves as much room as possible. So let's make another spike, right? So also let's sort of keep track of the locations we choose. So let's say this is like, you know, x1, this is x2 or something, right? Okay, let's make another spike. Let's put it here. Let's say that's x3. All right, and let's keep going. Let's make another spike. Oops, it's a bit wide. So let's say that's, you know, x4 is just where the peak of the spike is or something, right? And let's make even one more. Okay. And let's say that's x5, right? And then, so we keep adding spikes that get taller and taller. So what's the issue? Why can't we just keep doing this forever and end up with an infinite number of spikes, and then we'll have our unbounded continuous function, right? What goes wrong? Well, the problem is that because this function is defined on a closed interval, it turns out that basically, for some kind of deep reasons, there basically isn't enough room in this set to create an infinite number of spikes, okay? Because what will happen is these spikes end up clustering around at least one point in AB. Okay, so if you have a cluster, if you have like an infinite cluster of spikes near a single point, that's a problem, right? Because then obviously, you know, near that, the function at that point can't be continuous if there's like points, you know, arbitrarily close to it where the value just grows unboundedly, right? So that would cause discontinuity, and that's an issue. So how can we kind of formalize this idea that the spikes cluster around at least one point here? And what I do want to say also is that, so in general, the reason for this is that AB is compact. So actually, like, you can is compact. So you can actually state this exact theorem. There's an analog of this theorem when F is just defined on a compact subset of any metric space, and then you can show that it has to be bounded if it's continuous, and it's just the compactness that actually gives you that. Because basically, if you think about it, like, what you can do is you can use the spikes you create to make an open cover of this interval, and then basically you should be able to choose a finite subcover, but then that tells you that basically an infinite number of the spikes are like contained in some particular neighborhood or something. Or I don't know, that's kind of a rough-handed way of talking about it, but basically the compactness ends up being the real reason here that this phenomenon happens. But for our purposes in the proof, what really the way we will describe it is that if you think of the peaks of these spikes or whatever as forming a sequence, then because they're, it's a bounded sequence by the Bolzano-Weierstrass theorem, there has to be a convergent subsequence. And the limit of that convergent subsequence is going to be kind of a cluster point for the spikes that we created, basically, okay? So, so this really happens because of the Bolzano-Weierstrass theorem, at least in this case. In the more general case, there's, an argument you can make using compactness that will tell you that the function has to be bounded. Okay, so let me kind of write down the argument a bit. So, so here's the actual proof. Suppose f is continuous on AB and unbounded. Right. Then for all n, or let's say for each n, this may be better wording. For each n in n, we can choose choose xn such that f of, let's say, absolute value, sure. Absolute value of xn is greater than n, right? Because basically for each n, the idea is that, n itself cannot be an upper bound on the absolute value of f because f is unbounded, right? If f is unbounded, little n is not an upper bound. That means we must be able to find a place where the value of f becomes bigger than little n in magnitude. So that's the place where f becomes bigger than n in magnitude is what we call xn, okay? At least one of the places, right? So we can form a sequence this way. So xn is a bounded sequence. So by the Bolzano-Weierstrass theorem, there exists a convergent subsequence. Say, let's see, sure, x naught. Say xn approaches x naught, right? Then since f is continuous, f of xn approaches f of x naught. So absolute value of f of xn approaches absolute value of f of x naught, which is a contradiction, right? Because we actually constructed the sequence xn such that absolute value of f of xn clearly approaches infinity. Okay. Oh, and what I should say also is this, so x naught must be in AB because AB is closed. So see, we used both the closed and boundedness properties of AB here, right? Boundedness of AB was important because that's what actually let us apply the Bolzano-Weierstrass theorem, right? Because the boundedness of AB made sure that the sequence xn was bounded, right? So then we could apply the Bolzano-Weierstrass theorem, but then the closedness of AB was what let us say that x naught was actually an element of AB. So both the closedness and boundedness were critical, and that's, together those are what guarantee the compactness of the set AB. So compactness in the more general setting is the true expression of what's necessary to force f to be bounded. Okay, so we've shown, so f is bounded. So what about this business with maxima and minima, right? So proof that f achieves maximum and minimum on AB. So, set, let's see, what do they call it? M, sure. M is the supremum of the set of values of F. So this is our sort of, what we believe will end up being the maximum value. Right now, like the way it's expressed, obviously it's not guaranteed just from looking at it that F actually achieves this value, right? Because there are plenty of sets of real numbers whose supremum is not actually an element of the set, right? Also, I just want to say that like this set here, I might start writing in the future as F of, so supremum. So the supremum is outside, obviously, but the set here, let me just actually switch colors or something. So this set, I might sometimes write as F of A, B. Okay. In general, if you have a set A, then the notation like F of A is just like the set of all values that F achieves when you plug in any point of A, basically. So that's kind of common notation that I would like to be able to keep using in the future. But anyway, so we'll take M to be the supremum here, and then basically we can do pretty much the same thing we just did, right? Like if you look at this picture, imagine that we were playing this game, but instead of trying to make these spikes grow unboundedly, we just tried to make them get closer and closer to the supremum, but without actually touching it, right? Because that would basically be the only way for F to have, for the values of F to have capital M as the supremum, right? The values of F are supposed to have capital M as the supremum, but if they're not supposed to achieve the value capital M, then they just have to get like closer and closer and closer to it at different places in the interval without actually touching it, right? So if you imagine we were just trying to do that instead, say this was like capital M, right? Then we're just trying to get closer and closer and closer to capital M, but we need an infinite number of spikes to actually do that. And so the same thing is going to happen where there's going to be some clustering point. And then at the point that they cluster around, the value of F actually will have to equal the supremum. So let me just lay that out. So then for each n, there exists an xn, right, where F gets closer and closer to capital M. So xn such that m minus 1 over n is less than or equal to F of xn less than or equal to m. I guess we can say less than here. It doesn't really matter. So, right, and the 1 over n we just chose because that's a sequence that converges to 0. So this is forcing F of xn to get like arbitrarily close to capital M, right? So then there exists some subsequence convergent, right? xnk. Say, oh, I think I might have made a mistake back here. This should have been xnk, sorry. Anyway, so this is xnk, it's k approach to infinity. This should all be xnk. Right. Anyway, yeah. So hopefully it's not too hard to see that when you pass to a subsequence, none of the rest of this stuff is violated. Sorry. But anyway, right. So there's a subsequence x and k, and which converges to a convergent subsequence, and say it converges to x and k, converges to x1, I guess. I don't know, or x2 was actually the notation I used before, I think. All right, whatever. So yeah, then, f of x and k converges to f of x2, but by construction, f of x and k also converges to m, right? Because we forced xnk to be in between m minus 1 over nk and m, right? And that approaches 0, obviously, so it's sort of squeezed into approaching capital M. So f of x2 equals m, which is the maximum of f of x for x in AV as desired. And then the case for the minimum, or the proof, let's say, the proof for the minimum is similar. Okay, so as the very last thing I want to mention here, I'd just like to point out that, so that was theorem 18.1. So theorem 18.1 breaks completely if f is not, or rather, sorry, if we only consider f defined on AB. Okay. Now, of course, right, if you take a continuous function on a closed interval, right, AB, and then you just like throw out A and B from the domain and end up with an open interval, then of course that continuous function will still have to be bounded at least, although it still might not achieve its maximum and minimum anymore after you throw out A and B, but it'll at least be bounded. That's just because it had to be bounded before you threw out A and B. But what we're saying is that if you don't know that f came from restricting any other function, like if f could be a function that is only defined on this open interval and didn't have any other values anywhere else beforehand, right? Then f is actually allowed to be not only unbounded, but or not only, it might not only, not achieve its maximum and minimum, it might be unbounded. Okay, so for example, on 0, 1, f of x equals 1 over x is unbounded. And f of x equals x is bounded, but does not achieve a max or a min, right? Because the supremum of the values of f of x equals x on this interval is just 1, and the infimum is 0, obviously, but it never actually achieves those values on the open interval because those points are deleted from the domain. Okay, so don't just, don't assume that just because you're looking at like this interval of finite length that a continuous function has to be bounded or it has to achieve a max or a min or whatever. It may do none of those things. Okay, so this is actually a really important warning. Beware. Continuous functions are wild beasts. Okay, we're going to see a lot more weird behavior from continuous functions. Okay, so don't treat them like your friends because they can do some wacky stuff. All right, anyway, so see you in the next part.